Hey guys. Hey. I'm not using OpenAI anymore. It's just annoying as fuck. Going to charge this. I hope you guys can see. Holy shit. We can see. Let's go. Um, so this will be that is really good. Really good. I'm really happy for this. I'm not going to use ChatGPT anymore because I tried I spent like 10 minutes behind it and man it didn't understand shit. Anyways, let's have um okay, can you do one more favor? Don't do have don't have 1.5.3.1, 1.5.3.2 and stuff. Have 1.5.3, yes, then begin with section 1, section 2, section 3 and so on. And the same goes for 1.5.4. Dude, DeepSeek is so good. Man, these Chinese researchers, the Chinese mathematicians who did DeepSeek, thank you. Thank you that they exist. Dude, you don't even pay for this. Do you understand? You don't even pay for this. Like, if there was an option, I would gladly pay. Like, I know it here is like $33, 34 Canadian dollars. It's cheap, but why would I pay 34 Canadian dollars when I have to do most of the work? Look at DeepSeek, it's like very smooth. This OpenAI, they can't even run. Are you still writing? Oh, okay, you're done. All right, so just explain slowly what is going on. What do I have to know? Yeah, that's fine. That's fine. I'm not really concerned about it. So we have done this. I'm going to remove the title actually, and I'm going to keep the rest of those. We are also going to remove the date. Which one's the date? Um, we're going to focus on that later. Anyways, let us begin. We're going to do around 2 or 30 minutes. So can you explain easy what is going on? Can you explain slow, easy, slow, easy, less English, more math? What is going on? What is going on? Like, what do I have to understand? What do I have to understand? And yeah, that's, for English, only use the core explanations. Nothing much. All right, so and convert this to latex code now. Convert all this explanation into latex code. No, I meant only the one you explained just now. Just now you explained, right? Step one, two, three, four, whatever you explained just now. Don't convert everything. Just convert what you explained for the image into latex code. That's only for section one. This is goated, I swear. This is goated. Get in. So dynamic pressure, we know that Q is equal to half rho v square because, okay. Also, one more thing. Is it possible to explain again thoroughly, less English, more mathematics, in correlation to the hypersonic missile? No, less English, have English. I'm not saying I don't have English. That's fine. but the only English explanation will be the core explanation of the section image and have maths and convert it into latex code. This is really good. This is really good. Like I'm surprised what like I'm really surprised what DeepSeek can do. Like I'm really surprised. So a hypersonic missile experiences extremely large dynamic pressure due to rho v square. A small disturbance creates a large rolling moment, which generates side slip. So stability requires a negative rolling moment coefficient Ct of beta. That's the coefficient for the side slip angle in correlation to the thrust to restore equilibrium. So the development, so dynamic pressure Q is equal to half rho v square. For hypersonic missiles, V is usually greater than 5 Mach, and the Q will be very large. Why? Because if my velocity were to be, because what do we know about velocity, by the way? So what do we know about velocity? I mean, we did this in the previous one, right? So if my velocity were to increase and now I have Q is equal to half rho v square, obviously now they're measured in Mach, then, okay, I'm just going to get coffee quickly. So we know that V's So if the velocity increases, then obviously if I have q is equal to half rho v square, then obviously the pitch rate will increase. So the q being, sorry, not pitch rate, the dynamic pressure will increase. And for a hypersonic missile, obviously V is greater than 5 Mach. Now they're measured in Mach. 1 Mach is actually whatever the velocity of the, so Mach is measured by whatever the velocity of the missile is divided by the speed of light, right? So for a hypersonic missile, usually the velocity is greater than 5 Mach. So obviously the Q will be very large. And the disturbances in correlation to the side slip angle or the bank angle, bank angle will not be zero. Bank angle is, what's the bank angle though? What is the bank angle? I think it's like going up or going down, right? Rolls forward, rolls around its forward pointing axis. So is it like going up, going down? If I were to, uh, I'm focusing in correlation to the hypersonic missile. Hypersonic missile. The bank angle for a hypersonic missile is symmetric, like a cylinder or a core. It does not have wings level. So what phi means, the missile rolls around its long axis. So lift, if any, points in some reference direction. I still don't get it. I still don't understand. What is the bank angle? Okay, let's see bank angle. So left or right? So it's moving left or right. So oh, it's like tilting. So it's kind of, it's tilting left or tilting right. But I don't think I don't think missile is symmetric. Yeah, but it is fins. Oh yes. So bank angle will not be zero. This means the lift vector tilts. Um, the hypersonic missiles has fins. They have fins that move. I mean, not move. That allows the missile to bank, producing horizontal or vertical force. So lift of horizontal would be L sine of phi, which is L phi, because if phi is not equal to 0, now this L sine of phi is approximately equivalent to L phi, because if I have phi being such a very small value, if I have phi being such the sweetener, so if I have phi being such a very small value, then obviously I'm going to have sine of phi being almost equivalent to 0, right? That's the side slip angle. So the side slip growth rate would be beta dot, would be the coefficient for lift multiplied by rho, multiplied by the reference area, multiplied by the velocity, divided by the 2 times multiplied of the pitch rate. This M is the mass, this M is the pitch rate. Since V is hypersonic, even small amount of phi will cause large amount of side slip growth rate. Now, what is so few things to consider. One is that Q is equal to half rho V square, and I know that phi is not equal to 0. This means that, like in a missile, you're gonna have the fins, right? Those fins will will tilt so that it can either move left or move right. So fins will tilt so that it moves left or right. Let's look at ChatGPT now. it is very bad. I don't know how do you, people even put up with this as expected. I don't have to even have to look now. But yeah, um, because the fins will tilt, then obviously they will not be zero. Like 99% of the time, fire will not be zero because this is a hypersonic missile. Hypersonic missile. And it is a hypersonic missile, so you're going to have deviations every second. Every infinitesimal time step will have a deviation. Let's say t equals 1, 0.1, not 1. 0.1, 0.1, I'm going to have one deviation. 0.2, I'm going to have one deviation. Obviously 0.1 to 0.2 is very fast. So every single time you will have every single deviation. So every movement, it's like break them into sections. You can have like, it's like saying if you go on a road, right? You have those dots. So it's like as you go closer, if you keep going further and further, the dots that the speed dots, the distance between them will get closer and closer and closer and closer and closer. It's kind of like that. It's like a melody, right? It's like a music. And since V is hypersonic, even small amount of phi will cause large amount of beta dot. And rolling moment from side slip, so the rolling moment L is equal to CL of beta, the rolling moment in correlation to the side slip angle multiplied by the side slip angle multiplied by the pitch rate, the reference area, and what's B? Or B is the reference span, so reference span, reference area, the dynamic pressure, the side slip angle, and the coefficient for the rolling moment in correlation to the side slip angle. All right. No, I know. I know. All right. Section 2. Let's, you know what? Let's open two codes. I like what he's doing. This is for uh, now section 2. Oh, sorry. I'm gonna copy it until here, and I'm going to. I know why. I know why. Because I said end document. I'm gonna add this here. Because no, it's my fault. Because because I said end documents. When you do write end document here, it you know pretty much leaves that as comment, so that doesn't get printed out. Put a star here, and this was section 1. So this is section 1 core explanation. Core explanation. Let's move to section 2 now. This will be section 2. Suppose the hypersonic missile experiences a wind gust disturbance. The missile develops a rolling motion. The missile develops a rolling motion. Phi is not equal to 0. The biggest mistake I did was bought Nescafe, the darkest roast. Because I'm used to drinking the coffee that you need to boil and stuff like that, not instant coffee. So the missile develops a rolling motion where phi is not equal to 0. Phi is the bank angle. Bank angle. So as the missile banks, the lift vector tilts sideways, and so generating the lateral side slip motion. This introduces that beta is not equivalent to 0. And for a stable hypersonic flight, the missile must automatically generate a restoring rolling moment. Okay, easy, calm, what is going on? Like easy, calm, step by step. Calm, step by step. Easy, calm, step by step, so that students understand what's going on. What is going on? Um, Less English, more maths, and the English I want to see is the core explanation of the image. And just copy this. This is really good. This is really good. Um, did I copy with the okay? I copied with the section. No worries. Um, oh, that's too far. My bad. Section 2 here. All right. So wind gust makes a missile roll. So obviously the wind gust will make the missile roll over because unlike because if you look at a rocket or if you look at a missile, they don't have wings. So wind, so they don't have wings like airplanes have wings or jets have wings. Rockets don't have wings or missiles don't have wings. So if I were to like stay like that, like this is how my missile is, right? This is how my missile is. And obviously if the wind blows, it's like you're rolling, right? It's like, if you have like a bread that you can flatten it, if you have a bread that you can flatten it, you can do the rolling thing or whatever. Like you have yeast and then you roll it, kind of like that. Kind of like that. Because it doesn't have the wings to force that, to push that wing upwards and then create a back. It doesn't have that. All it has is a rolling. So this is why when you launch a missile, or when you launch a rocket, it sometimes spin because like in an airplane, like you have wings, right? So it kind of streamlines, and then when it hits the bottom part of the plane, it pushes it upwards because the wings are also there. But in a rocket or in a missile, it doesn't have wings, so rather than like tilting it upwards, it's going to kind of create like a rolling motion. You roll, like roll, yeah, like that, roll. So the wind gust cause rolling motion, so which means phi is not equal to zero, so you have a bank angle. Now, bank angle in a missile and bank angle in a plane are different. Bank angle in a missile is rolling. Bank angle in a plane is actually banking to the right or banking to the left. So technically, we are saying rolling to the right, rolling to the left, rolling to the right. And the lift vector magnitude, so lift is equal to the coefficient for lift multiplied by the q, which is the pitch rate, not the pitch rate, the dynamic pressure, which is half rho v square, multiplied by the reference area. After banking, lift has a sideways component, so L side. This is the best explanation. I swear to God. I swear, I swear, I swear. I swear to God. I swear to God. This is the best explanation I received. The best. The best. So what happens is wind gusts will cause a rolling motion, right? So we're gonna have phi not equal to zero. Cool. And the lift vector magnitude, so we know the equation for the lift vector magnitude, where L is equal to the coefficient for the lift multiplied by Q, which is half rho v square, multiplied by the reference area. And so after banking, the lift will have a sideways component. So now L side will actually be L sine phi. The reason being is because now it banks. Although yes, the missile rolls, but it is still banking, right? The only reason it is banking is because the wind pushes the missile, so which means it's going to roll over. It's not going to stay with you. It's not going to go straight because you are going to have wind. Anything like you're going to have wind, you're going to have aerodynamic uncertainty, you're going to have thrust variations. Maybe like if you look at a missile, like it doesn't have to necessarily be by the wind. Maybe if you have like, I don't know, 5 or 6 engines. If you have like my if you have like if you have like 5 or 6 engines, right? So let's say for example you have 5 or 6 engines. Cool. And what happens is that even if you have 5 or 6 engines, maybe like the left half, the left half, let's say, that is working. Like that is working perfectly fine, and the right half is working, but not as powerful as the left half of the engine. And so what will happen is that because the left is creating more power as compared to the right, obviously you're gonna have this little banking, right? Because one side is less, the other side is more. It is pretty simple. And banking can also be occurred due to that. And because it is rotating in this sense, and so there's an angle, right? So because rotating, every rotation will have an angle. How much angle, like if we were to look at a plane, it's very easy to understand because obviously you can just, if it tilts up, if it tilts, then you're just going to see, okay, what the initial angle was and the angle currently at the moment. And maybe if you have an image, you can use a protractor, but for a missile, it's pretty difficult because you can't just do that, right? Maybe you can. I'm not sure. Maybe you can. Yeah, you can actually. So the sideward force causes the side slip acceleration. So MA would be L side, which is equal to L sine of phi. So this is your acceleration. It will cause acceleration, right? It's going to cause acceleration because it's kind of like a plane, right? So if you look at a plane, um, if it banks to the left, so it's going to create an acceleration to the left. It's not only going to go front. Will it? I don't think it can. And the reason it won't is because now, like if the plane is banking to the left, then obviously it's not going to go. It is going to accelerate. 100% is going to accelerate because like on one hand, like there's a wind that's creating more power in addition to your already powerful engine, right? So it's going to create additional acceleration, but it's not going to go straight. It's going to go towards where it's banking. So if I were to bank to the left, then I know that it's going to go either left, so it's going to rotate, or if the bank, it also depends on the nose, right? It also depends on the nose. So if it's like banking to the left, but it's nose up, then it's going to go up, but after some time it's going to come down, right? And if it's down, then obviously that's it will go down. So the L side, so, L side, so whatever the side it is focusing on, the lift. So this L side means lift, yes, lift, but not straight. L is like lift, like normal lift. L side is lift towards the side, so either side. And so sideways force causes side slip acceleration. So I'm going to have MA is equal to L side, which is just L sine phi. And obviously I know that beta will not be zero. And the reason beta will not be zero is, I mean, if it's banking, there is no way you're going to have a side slip angle of zero. It's impossible. Because you must understand that the side angle, like the phase angle, is in correlation with the bank, right? So the bank angle. Now, if you have a bank angle, that automatically tells you where the plane will pitch up or whether the plane or rocket or whatever will either pitch up or pitch down. And in 100%, I don't know if it's 100%, but in rare cases, it's not going to be bank and then straight throughout, unless 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 you have this, let's say for example, if it's banking and then there's no engine, and so what you do is actually you switch off the engine, and then now maybe it could be due to the wing, maybe there's no wing here, or maybe the wind gust is so high that forces the airplane to actually lift it, I mean not lift, um create this bank angle towards the left. and maybe there's no wind here. I mean, there's no wing here. There will be less engine power here, more engine power here, and so it'll try its best to stay straight because you're not applying much engine here. Like you're not applying much engine force towards the left. You're applying more engine force towards the right, which for a few seconds it's gonna stay straight, and then it'll try its best to come up. It'll try its best because now you don't have a wing here, right? You don't have a wing. If you have a wing, that's fine. If you have a wing, that's fine. But if you don't have a wing, it's going to stay like that for a few seconds, and then it'll try its best to climb up, or it'll try its best to lower down the side slip angle because you don't have a wing here, right? But in the case of missile, it's kind of little different because in a sense, like a plane moves to the left, the missile you don't say moves to the left or banks to the left. You see it kind of rolls to the left, right? It rolls to the left. And so the rolling moment equation. So L is equal to CL of B. So that's the coefficient for the rolling moment in correlation to the side slip angle multiplied by the Q, which is, sorry, not Q, beta, which is the side slip angle itself, multiplied by Q, which is the dynamic pressure, which is half rho V square, multiplied by the reference area, multiplied by the, what was B again? I forgot. Reference span. And so the stability condition, the restoring moment, that the coefficient for the lift in correlation to the bank angle must be less than 0. When beta, the side slip angle, is greater than 0, then it must be negative. It must act opposite to where it's currently been banked, right? So if the bank is towards the left, then I must make sure that the coefficient for that rolling moment, because it's rolling, right? And we're focusing on missiles. And the coefficient for the rolling moment, whatever the value I get for the coefficient of the rolling moment, I must have a negative value then. Because if I were to have a negative value, so it's like saying that let's say the bank angle is, I don't know, 47 degrees. And okay, let's say the bank angle is 47 degrees. And the coefficient for the lift in correlation to the bank angle is, let's say, minus um, 41 degrees. Minus 41 degrees. And so now you're going to do 47 minus 41, which is 6 degrees, right? But you see that 41 degrees have been, it's kind of like saying 41 degrees has been removed from the 47 degrees. You subtract it and it kind of, straightens it, right? So it must be less than 0 because the coefficient works complete opposite. So a few summaries. So phi is not equal to 0, meaning that the side uh, rolling moment will be L sine phi, the rolling moment multiplied by sine phi, which means beta is not equal to 0, which means you need to ensure that the coefficient for the lift in correlation to the bank angle must be less than 0, right? Now you must consider that the side slip angle will not be negative, because if it were to be negative, then you're considering that I mean, in a missile, you never consider it negative because you can't. Because even if the missile is like that, even if the missile is like this, it's still the same thing. But for a plane, the side slip angle being negative, the plane will be upside down, right? The plane will be upside down, which is obviously, why would a plane be upside down, right? A really good explanation. Really, really good explanation. Like, I don't understand like how easy could I have understood now. Okay, easy, calm, step by step. Don't miss. Okay, easy, calm, step by step. What is going on? Again, same explanation, same way explanation. Come on. I'm enjoying this. Ashan, Ashan. Just want to make sure if Valentine is okay. That's all I want to know. Like, I just want to make sure if Valentine is okay. Just switch on the light. I don't know if this light works. Oh, 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 let's go. Oh, oh, there. Just wait, just wait. Okay, let's continue. Holy shit. All right, anyways, let's go, let's go, let's go. Section 3. Come on, boys. Come on. Come on. Section 3. All right, so the core explanation, the rolling moment coefficient tells us how much the missile wants to roll. For stability, when side slip beta is positive, the coefficient of L must be negative. What does one view mean on X? Someone, okay. Okay. So at the moment, I have two views. Does that mean someone saw? Like, as in two people saw, or I count two? Oh no. But I clicked on it 8 times. It still shows 2 views. No, 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 no. No, I meant 2 views means someone saw. Okay, I just want to comment on Valentina Gomez's post, and I want her to see the comment. That's it. But I am the only one who commented though. No, don't see any quality spam, whatever. No, I just wanted to check up on her, see if she is okay. Oh shit, I got 40 followers. That's so cool. Man, I can't even. Aw. Anyways, alright. I'm worried, man. Anyways, no worries. So, The rolling moment coefficient tells us how much the missile wants to roll. For stability, when side slip positive slash side slip is positive, the coefficient for the rolling moment must be negative. This brings the missile back to wings level. So coefficient for so coefficient for so the coefficient for rolling moment is rolling moment divided by half rho v square s times b. So rolling moment, reference area, reference wingspan, the aerodynamic density, the velocity, and half. Right. So we can also write the coefficient is equivalent to L divided by QSB. Right. So because that itself is Q. Now, how coefficient of lift changes with side slip? So the coefficient of lift in correlation to the side slip angle is equivalent to the partial derivative of the coefficient lift in correlation to the side slip angle. Because if I were to look at the coefficient of the lift, it is equivalent to L divided by half times rho v square s b, right? And all those variables and stuff like that are part of the coefficient lift whatever, and so you typically have to partially derivate the angle leaving everything constant. And so the stability condition is that if for it to be a stability condition, you must make sure that the coefficient for the lift in correlation to the side slip angle is less than 0. So what this condition means, if beta is greater than 0, then the coefficient for lift must be less than 0, meaning the rolling moment must be less than 0. Can we do an example? Let's do an example. Let's do a maths example. Let's do a maths example if that's all right. Yeah, let's do a maths example. Firstly, can you fix the table? Sorry, my bad, my bad. So firstly, fix the table. Firstly, can you fix the summary table if you don't mind? Secondly, let's do two mathematical examples in correlation to section 3. Are going to be 3.4, then 3.4 multiplied by 1 meter 400,000. That explains everything from coefficient. And so C of n measure mostly obviously, but that explains R going to be 3.4, then 3.4 multiplied by 1 meter 400,000. That explains everything from section. And so C of n mostly so Right. Again, did you do the pretty worried, not gonna lie. I'm worried because I'm like I know Valentina loves someone else. I know that. I know that. I am aware of it. Like I just wish I was not aware of it. I wish I was never aware of it, but I'm um well, you have these two examples. These two examples, could you convert it to latex for these two examples you just did? These two examples you just did. Can you convert it to latex code? But yeah, so I'm just going to copy this here. DeepSeek is really good. DeepSeek is really, really good. I know why. I know why. I know why. I know why. Let's leave it there. So stable missile. So for example, the stable missile when the coefficient for the lift, I mean, not lift, coefficient for the rolling moment in correlation to the side slip angle is less than zero. So for example, that the coefficient for the rolling moment in correlation to the side slip angle is minus 0.05 because obviously it must be negative per degree. Per degree means for every degree change, it'll be so. Let's say, for example, if it's minus 37 degrees you want to change, then it's always going to be minus 0.05 minus 0. So minus 0.05 times 37, right? Something like that. And so it will be minus 0.05 per degree. Beta is 2 degrees, so side slip to the right. And the pitch rate, I mean, not the pitch rate, the dynamic pressure, the hypersonic dynamic pressure is 500 K because for a hypersonic missile, the pressure will be extremely high because it's not only narrow, but it is extremely fast. The reference area will be 0.5 meter per second square, and the reference wingspan would be 0.8 meter. Define CFL. CFL is the coefficient for the rolling moment. So the coefficient for the rolling moment is equivalent to the coefficient for the rolling moment in correlation to the beta angle multiplied by the beta angle itself. The beta angle is 2, and the coefficient for the rolling moment in correlation to the beta angle is minus 0.05. So minus 0.05 multiplied by 2, which is minus 0.1. And now we need to find the rolling moment itself, which is L is equal to the coefficient for the rolling moment multiplied by the dynamic pressure multiplied by the reference area multiplied by the reference wingspan. And so what's the coefficient for the, we found it minus 0.1, 500,000, 0.5, 0.8. Right, and then you do all those multiplication and whatever, and so negative rolling moment, it means it's going to move to the left, and side slip is right, but the missile rolls to the left, and this opposes the disturbance because side slip is to the right, or but your the movement of the rolling motion for the missile is to the left, right? If your rolling moment is to the opposite, if your rolling moment is opposite to the side slip angle, then you're stable, then you're good to go, it will be stable then. But if your side slip angle is the same as the rolling moment, then it is not stable, and the only thing there you can do is manually add extremely high value to make sure that it remains stable, right? Because it's a hypersonic missile. Same procedure. So positive means rolling right, side slip angle is plus 2 degrees, and missile also rolls in the same direction. So there is a disturbance. So the missile will tumble around. So case result. So if the coefficient for so stable, obviously these are the stable values. So minus 0.05, 2 degrees minus 0.1, minus 20,000. So which means your rolling moment is minus 20,000. So it will be stable. It is stable. Like yes, yes, it is rolling to the right. Granted, but this also means that it's also able to stabilize the missile. So it will be able to stabilize the missile. But for an unstable one, if it were to roll to the right, but then when I did the measurement and when I did the calculation and stuff, I end up having my rolling moment being to the right, being positive. And so obviously it's not going to be opposite to what the actual rolling moment, like where it rotates towards or rolls towards. It's going to, like, if I have the rolling direction as the same as my rolling moment, then it is dangerous. If I have the rolling moment opposite to the rolling direction, or the, sorry, not the rolling direction, the side slip angle, then if it's opposite, good. Same thing, bad. Section 4. Let's do section 4. Yes. Let's do section 4. Let's do section 4 and section 5 together. Can we do section 4 and section 5 together? Can we do can we do these two sections together? Jose Mourinho. special one. Jose Mourinho. Anyways, so let's do section 4. Let's do that. That's really good. That is really good. Man, I don't. Yeah, this is section 4 and section 5. So obviously it's going to look big. We're doing section 4 and section 5. I have a feeling that I had end document. No. So section 4, the bank angle and side slip growth. So core explanation for the image. So when the missile banks right, so phi is less than greater than 0, the lift vector tilts sideways. The sideways component L sine phi pushes the missile sideways, creating a side slip beta. At hypersonic speed, the velocity of the hypersonic missile will be greater than 5 Mach. Even a small change in bank angle will create a huge side force because Q is proportional to V squared. Now keep in mind, velocity is very high. Velocity is very high. Velocity is the independent one here. And if you were to, and the velocity will be extremely, extremely high. If the velocity is extremely high, you square that, it's going to be much more high. And obviously, that is proportional to the dynamic pressure. So the pressure will increase more. So missile banks right. So it doesn't bank right, it rolls to the right. So phi is greater than 0. Now, lift vector before the banking will be L is equal to the coefficient, the lift will be equivalent to the coefficient for the lift multiplied by the Q multiplied by the reference. Oh, shit. Oh, why isn't it charging? Oh, come on. Good, 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 good. All right. So before the banking, so you're going to have lift is equal to the coefficient for the lift multiplied by Q multiplied by the reference area. After the banking, the lift will decompose. So vertical will be cosine, sides, so sides as in this, will be sine phi. So cosine phi, sine phi. And so the side force causes a side slip acceleration. So we're going to have the m times a, which is the L side, which is L sine of phi. So side force causes side slip acceleration. Okay, I still didn't understand this. Is it possible, like, can we do one example, like, just to better understand? Because there are a few things that I didn't understand here. Is it possible if we can do like two examples, just two examples? Is it possible if we can do two examples correlating to this, please? I understood because you explained it easy, but at the same time, we're streaming, right? But at the same time, I didn't understand. Oh, I'm just going to go a bit back. That is huge. At the same time, I didn't understand. The same time, I didn't understand. So let's do two simple numerical examples. Um, we did this. Convert these two examples into latex code. Convert these two examples into latex code. Mention it here. Don't add end document. Here. At least as far as I know, like the country where I reside in, Qatar, like I haven't seen anything wrong with that. Like, dude, Qatar is like, nah, man, you can't say shit about Qatar. Not because I'm restricted, but because I haven't seen anything bad. Subsonic or supersonic speed baseline. So, given that the coefficient for the lift is zero point 0.3, the air density is 0.01, velocity is 300 meter per second, so it's around like 0.88 Mach. Um, S is 0.5 meter per second meter square. M is 500 kilograms, and phi is 2 degrees. Now you can do NP or radians too, right? So dynamic pressure Q is equal to half rho v square, so half times 0.01 times 300 square. And the lift force will be L is equal to coefficient for lift multiplied by the dynamic pressure multiplied by the reference area. And the side force on the blank bank angle. So the lift coefficient. Lift from the side is equivalent to L sine of phi, so 67.5, which is the 67.5. Oh, that is the lift force. So lift force multiplied by sine of 2 degrees, so 0.0349, so 67.5 multiplied by 0.0349 degrees, whatever the LZ value is, and then you use the side slip growth rate. So these are the core equations. Where are the core equations? So the core equations are the dynamic pressure, the lift force, the side force from the bank angle, and the side slip growth rate. These are the equations. Literally, these are the equations. Same thing. Core explanation for the vertical tail contribution to lateral stability. So the vertical stabilizer generates a side force Y of V when side slip uh, beta occurs. This force acts through a moment arm R, producing a rolling moment L. The stability derivative, the coefficient of the rolling moment in correlation to the side slip angle, depends on the tail's effectiveness, eta of V, and the volume coefficient. Stability still requires that the coefficient for the coefficient for the rolling moment in correlation to the beta must be less than 0. Okay. Um, what is Y of V again? A side force. So side force will be Q times S of V is what? What is S of V? Of vertical, so side force is equal to the dynamic pressure multiplied by the vertical tail area multiplied by the not vertical, vertical tail area multiplied by the side force coefficient derivative in correlation to the beta angle, not beta angle, side slip angle multiplied by the side slip angle. So this force acts through the moment arm. So the moment arm rolling moment would be the vertical stabilizer. So I'm sorry, side force multiplied by the moment arm. So moment arm multiplied by the side force is equivalent to the rolling moment. And then substitute y into this. So y is this whole equation multiplied by r, and then the coefficient. So y of v is the vertical stabilizer. No, y of v is not the vertical stabilizer. Y of v is the side force. So y of v is the side force when side slip beta occurs. When side slip beta occurs. This force acts through the moment arm to produce a rolling moment. So side force creates a side slip when side slip occurs because it's kind of like you're rotating and it's going to turn it to the left. It's kind of like that. So because when the think of it like a piston, right? Not piston. It's kind of like a rolling or roller or whatever. So it's like if you kind of rotate, right? You have a certain angle, and at the same time, it's going to bank to the right or to the left or whatever. So that change in angle is what you call beta, the side slip angle. And the side force, while V, that doesn't count on the angle, that counts on where did bank, like did it bank or like, there's this force that creates, right? So it's going to bang to the right or bang to the left. Like in most cases, if we were to use the example, they're going to say bang to the right. So this force will act through the moment arm R to produce a rolling moment L. The stability derivative, the coefficient of L in correlation to the beta, depends on the tail's effectiveness eta of V and the volume coefficient V of V. The stability still requires that the coefficient for the rolling moment in correlation to the side slip angle must be less than 0, as usual. So y of v will be equivalent to half rho v square multiplied by the s of v. That's the vertical tail area multiplied by the Cy of beta. Cy of beta is the side force coefficient derivative in correlation. So technically it is curl C of y by curl beta. The partial derivative curl C of y divided by curl beta multiplied by the angle itself. This would be also be the same thing. So S of V would be curl of S divided by curl V. And then YV would be curl of Y divided by curl V. And so this force will act through the moment arm. So this side force, sorry, I'm screaming. So this moment force, this, I mean, a moment force or the side force will act, will be part, will play a role alongside that moment arm. And because of the moment arm, and then you multiply it by the side force, it'll create a bank, right? So L would be the Y of V multiplied by R. So moment arm multiplied by the rolling motion. Mhm. People do see me. I like it. People do see me. It's just that I think Valentina is the only one that doesn't see. People do see me. People do see me. Devon. All right. So the rotating moment will be the side force moment multiplied by the moment arm. And so we're going to substitute y of v. So y of v is this equation here. And so the coefficient for the rotating moment will be, oh yeah, rotating, okay. L is equal to y of v multiplied by r. C of L is what? L divided by half rho v square times S times B. And so what I'm going to do is C of L is equal to y of v multiplied by r divided by half rho v square sb, and y of v, which is the side force, replace the equation. So you're going to replace this equation. So you're going to have CFL being, I'm just going to write replace equation multiplied by r divided by half rho v square sb. It's just going to replace the equation, because you're also going to have half rho v square. So half rho v square, half rho v square you can cut out. So then you're going to have SV of r divided by S of B. S of not S of V, S of B. And so that's the equation. And obviously the correlation for the correlation coefficient for the restoring coefficient for the rotation moment in correlation to the side slip angle will be the partial derivative for CFL, the rotating moment, in correlation to the beta. So including the tail efficiency factor eta v, so coefficient for rotating moment in correlation to the side slip angle will be eta of v multiplied by v of v multiplied by the um, coefficient for coefficient for side force in correlation to the beta angle. Let's do an example. Let's do an example. Let's do two examples correlating to both. Yeah, let's do an example. Let's do an example correlating to both of them. Let's do an example correlating to both of them. And how far are we? Nice, 1 hour 25 minutes. That's really good. That's really good. Uh, we're gonna here, boom. All right. Suppose aerodynamic surface contains dihedral angle. Okay, let's do a dihedral. Oh, wait. Wait, did you already do a dihedral example? Why did you do dihedral example already? Dihedral example? Okay. This dihedral example is different. Dihedral effect example. Actually, you know what? It's a good thing that it's there. How many steps are there? It's a good thing it's there. It's a good thing it's there. I'll just move it all the way at the end. No, wait. I'm confused. And where is this here? There's all those. There. So dihedral effect example. So how does dihedral angle tau create a restoring rolling moment during the side slip? So rho is 0.01 kilogram per meter cube, v is 2500 meter per second, s, which is the reference area, 0.5, and the what's the lift curve slope. What's the lift curve slope? So suppose the aerodynamic surface. Okay, let me just put a star here. So suppose the aerodynamic surfaces contain dihedral angle tau is greater than zero, and during the side slip motion, the change in the disturbance angle will be almost equivalent to the side slip angle multiplied by the dihedral angle. So it will create an additional lift, it will create a restoring rolling moment, and it's going to create improved lateral stability. Adaptive guidance system continuously estimate these changing aerodynamic effects in real time. So let's say a dihedral effect example. So how does dihedral angle tau creates a restoring rolling moment during the side slip? So given that rho is 0.01, v is 2500 meter per second, s is 0.5 meters square, the coefficient for lift in correlation to the angle of attack will be 0.1 per degrees, beta is 2 degrees, tau is 5 degrees, which means 0.0873, and y is 0.4 meters. And change in angle of attack due to the dihedral. So during the side slip beta, one wing sees increased angle of attack. So the change in angle would beta times tau. So beta is 2 degrees, tau is 10 degrees, so 5 degrees, so it is 10 degrees. So 10 degrees squared. So 10 degrees times degrees, which is degree squared. And beta and tau must be in constant units. And obviously it's going to be rad square. Oh, it's still going to be rad. Okay, it's still going to be rad. I thought rad square. I'm so stupid. So change in lift. So Q is equal to half rho V squared. So 31,250. Obviously, you measured that. The change in lift will be the coefficient for the lift in correlation with the angle of attack multiplied by the change in angle of attack multiplied by the dynamic pressure multiplied by the area, reference area from the strip. So del L is 0.1 degrees, 0.1 per degrees multiplied by 0.75, 0.175 because we did the conversion from degrees to radians. 31,250 multiplied by 0.1. 0.1 was the change in angle. Not change in angle, sorry, the change in, where is it? Oh God, what's S strip though? Assuming that the dihedral effect, okay, that's the dihedral effect is 0.1 dihedral effect area is 0.1 meter square. So we're going to say 0.175, 0.1, 31,250 multiplied by 0.1. You get the value, you get the dimensions and stuff. The rolling moment from the dihedral effect, the lift difference between the left and right wings acts through the half span y. So the dihedral for the rolling moment will be the change in the lift multiplied by y multiplied by 2, y the y-axis, right? And the only reason we say y times 2 is because although there are both wings, opposite signs. One is on the left, one is on the right. So you can have one is on the minus, one is on the plus, which means technically both of them act, right? You're going to measure all your dihedrals for beta greater than zero. So you're going to have an increased angle of attack, so more lift on the right. So to restore that, your coefficient for the rolling moment in correlation to the side slip angle will be rolled to the left. Yeah, I did them. Now, yeah, good stream. Boom.